It may suddenly occur with high traveling speeds, posing threats to human life and properties, including buildings, highways, and infrastructures. So for us, like academy or geotechnical engineer, what can we do to minimize this problem? Among various methods, the early warning system is considered to be one of the most promising way. And in this system, it requires a model that can predict when, how, where that this disaster occurs. And that is what we did. So this slide showing you the research gaps and research aims in my project. The literature review was presented in my confirmation presentation, so will not be repeated here. The gap one is existing early warning system lacks an advanced computational model that not only predicts the onset of failure, but also the distribution zone should the failure occurs for mitigation planning. The gap two is the current early warning system rely on symbol soil profile to make predictions, which result in less accurate forecasts. The gap three is the current early warning system consorts in utilizing the field data for rapid prediction and early detection of landslide. So based on the 3F, this is our 3 M's. The M1 is we develop an advanced computational approach to simulate entire rainfall new landslide process. The M2 is we develop a ground model to generate initial geological conditions from limited data. And M3 is we develop a machine learning framework for rapid prediction and early landslide detection. So based on the 3 M's, it was formed into 3 stages, which will be presented in this presentation. Step 1, I will talk about computational framework to capture the entire rainfall new landslide process. Step 2, I will present about ground model to generate initial geological conditions from limited data. And finally, I will present about step 3 is a machine learning framework for rapid prediction and early landslide detection. Step 1, firstly, we start by looking at how do we establish a mathematical framework. We consider an unsaturated RBE, which consists of 3 phases, solid, water, and air. And in order to establish governing equation for this system, we need to apply a homogenization process to each phase. And then from here, we then apply the mixture theory to establish governing equation for each homogenization phase, which consists of mass and momentum conservation equation. Now we're using the single layer approach that where we combine all governing equation to establish a unique governing equation for entire system. Consists of porosity change, seabed flow, and the motion equation. So to complete this governing equation, we need 3 things: hydraulic model, quantity model, and numerical methods. So for hydraulic quantity model, in this research, we are using very standard model, the Van Genogen model for degrees of saturation function, the Mueller model for water permeability function. In particular, we account for influence of porosity change on the soil water current curve, and you can see here. For quantity model, many existing quantity model developed in the literature can be straightforwardly incorporated into our framework. However, in our work, because we aim to develop something that's simple and applicable to both sand and clay, and therefore we actually select the Kaiser model and extend it to account for unsaturated soil behavior. For example, the LC curve, you can see here, describe how the reconservation pressure change with suction. So now if you're working in the area of unsaturated soil, there's a lot of literature discussing how compression curve evolve under different suction. Traditional approaches often assume this is a linear line, but experimental evidence they demonstrate that this compression curve is non-linear, and more importantly, they actually convert toward the saturated compression line as the airport flows. So to capture this important behavior, we propose a new compression index rule. This slide showing you the comparison of compression rule under X. At the top, we show you the original BBM compression rule, which is widely used in the literature. But keep in mind that we present within an effective stress framework. You can see here the result from BBM compression rule produce linear line and does not converge at such an increase. At the bottom is our proposed equation that allow us to actually describe the nonlinear and also converging toward the saturated compression line. Here's the model performance on dry compression test demonstrated using 2 different experimental data sets. One is for boulder clay and the other for compacted fluids. In the graph, the green line is represent model prediction, and while the circle or the diamond triangle lines here represent for experimental data. As you can see that our proposed model can accurately capture the nonlinear compression line and also the airborne pulse observed from experiments. So up to now we have mathematical framework, we have quantity model. Finally, to complete the governing equation, we need to solving the spatial derivative, that where we need to use numerical methods. So in my research, we use the XBET method to achieve that. So what is the XBET method and how does it work? So XBET is the continuum mastery method in which particles carry few variables and move with the material velocities. So let's look at this computation domain. This can be represented by a set of particles, and each of particles occupy a given space and move freely on a space. And when we want to calculate information of a particular location, we're using the interpolation process or weighting average. So after completing the framework, now let's verify our model. To demonstrate the performance of our model, we take these two experiments from literature conducted by Askari Nezat 2009 in Switzerland. At the bottom left is the cross-section. This is a 56 meter length and 36 meter height, and this is the top-down view. At the top right is a table showing information that enable us to calibrate the quantity model and solve the calibrated curve with their experimental data. At the bottom right is the XBET model setup. The rainfall is both on the surface particles using water floods. So here is the calibration of our solid calibrated curve. Because we're conducting the simulation for this replicant field, so it is important to calibrate the soil parameter at this location. You can see that we can fairly fit the one chain equation into solid calibrated curve using their experimental data. Here's the calibration of our quantity model. You can see that the quantity model can capture well the volumetric behavior and shearing behavior under both isotropic loading drain transfer test and isotropic loading undrained transfer test. So finally, once we obtain all parameters, we plug it into our model and try to predict. So here is the seabed prediction and volumetric water content. You can see that our numerical model can capture question 9, that's how potable pressure change with time at different locations, and also this is the evolution of volumetric water content with time. This slide showing you our model can capture the displacement response of entire failure process. So if you're looking at the top right diagram, the dotted red line represents for displacement sensor measure from experiment. The green line is the numerical result. So we can be able to capture very well the evolution of the slope failure both onset and also the failure area after the test, as you can see over here. So this is very important for early warning because if we know the onset and also the post failure, we can be able to alert the warning, and then from there we can evacuate people from danger zones. We also have successfully extend our model to 3D simulation. Here we verify again Denso et al. 2012 experiment. On the top right is the model setup that where rainfall is involved on surface particles. On the bottom left is the table showing information that enable us to calibrate the quantity model and show the calibrated curve that you can see here. Here's the model performance. We can be able to capture the evolution of section with time and the evolution of surface displacement with time. The results are very nice. And as you can see at the bottom middle, the animation here showing that how that water infiltrates into slope, the water accumulates and eventually causing collapse. This slide shows you the summary of step 1. We have submitted one journal paper to Computers and Geotechnics. Step 2, before going into detail this test, I want to briefly discuss the typical geometrical test used for ground modeling. So if you look at the image on the left, it is show an example of the soil profile. So for construction or slope design, it's crucial to understand the underground soil conditions. So this is why engineers often do the field test. So there are two commonly field tests. This is CBT and HBT. However, this data is often sparse and limited due to the budget or the scale of the project. Here we want to highlight the challenge. So if only limited data are available, how can we reconstruct the entire soil profile. So in my research, we use the compressed sensing and inverse distance weighting technique to reconstruct the entire soil profile. So first, let's look at this picture. Assume that we have the input measurement y, which is true borehole data. So what output that we want is the entire soil profile. So we call this the reconstructed F hat. So mathematically, we have y equal of CF. Y is mean that the measurement, this is the borehole data. The C is the measurement matrix, which is the location of the borehole. And F is route through, which is the entire soil profile. So even if you know Y is the borehole data, you know C the location, but F have infinite many possible solutions. So this is a well-known challenge, namely underdetermined problem. So how can we solve it? So luckily we can use the concept of the Fourier series. So any function f can be represented as a summation of sine and cosine function d multiplied by a coefficient x. For example, assume that we have one d function. The black line is the hidden ground truth data. The color line is the reconstruction solution. So if you're using one frequency, this is the result that you got. But if you're using multiple frequency, example like 2 or 5 frequencies, and you can have the better result. So the key idea here is, if we want to find the solution, it means that when we can find a good frequency components, then we can make a good solution. So here we're using optimization to find frequency coefficient that's subject to the measurement equation. So in addition to compressed sensing, we also use the inverse distance weighting technique for improving the computational efficiency. So basically this method estimates the unknown value based on the known value nearby. The closer points have greater influence. So now let's verify our proposed method using a real case study in Australia. So this is the project location, this is the target area. 6 red borehole here are used input for reconstruction. The 12 blue boreholes are used for validation. This image here shows the detail of the borehole from CVT, which is deep resistance. Here's the model performance. We present the process into 2 steps. Step 1 on the left, we input the 6 CVT borehole data into 3D space. And on the right, you can see the visualization of 12 boreholes used for validation. Step 2, using 6 borehole input here, we apply our proposed method and then we can reconstruct the entire 3D soil map. So we saw the detail of comparison reconstructed and the actual borehole data at a validation location. The red line here represents our solution, and the blue dashed line represents our actual data. So you can see that overall, the result demonstrates that our method is able to reconstruct the entire soil profile quite reasonable. In addition, we compare our results with the other method from the literature. Here the validation detail at the CVT F61, 71, and E54. The diamond here and the square lines here represent for the result from other method in the literature. So you can see that the red line again is our solution, and the blue dot is hidden actual data. So you can see that overall, the result demonstrate that from all methods, the result from all methods can fairly fit with the actual data, but cannot accurately capture due to the complexity of the soil profile. So for this reason, we now raise the other challenge. So what can we do to further enhance the accuracy of this reconstruction solution? And that is what we did. This slide will introduce a novel framework which extends the method I presented earlier. So here I will explain the key steps. First, we're using the input borehole data and apply our proposed method to generate the initial reconstruction. So it is important to know that many existing approaches in the literature, also the commercial software, can also achieve this. So what makes us different? That's what we have, the composition model. So by inputting the initial reconstruction solution into the numerical model, for example, we can simulate the soil behavior under rainfall and generate some predicted data. At the same time, we have monitoring data from the field, example like piezometer to measure water pressure. The key idea here is by using an optimization algorithm to minimize the difference between the numerical prediction and monitoring data, we can update the ground model. And this updated ground model is then again input to the numerical model and allowing to continuous refinements. So this is the entire picture of our proposed framework, which rely on an effective optimization algorithm. So in our framework, we're using the genetic algorithm. This is a popular method from evolution computation. The core idea is simple. The algorithm maintains the population of candidate solutions, and over multiple generations, it selects the best performing individuals and combine their traits to evolve to get the better solution. On the right, you can see that this is the basic flow of genetic algorithm. One critical part of this algorithm is that the error function, which tells the algorithm that how good each solution is, and this function is defined based on how good of the simulation matches with the monitoring data. This slide shows you how we verify our framework. On the left, you can see that this is a slope with a detailed slope profile generated from random field theory. This resembles hidden gravity data. So from this, we then dig some boreholes, and borehole from B1 to B7 here are used as input for reconstruction, and the B1 here used for validation. So on the right, you can see that we saw the same slope, but now only 7 boreholes visible. The purpose of this setup is to generate the numerical case study, just like a real-world application. So here's the more performance of our proposed framework. First, on the top left, this is the borehole input. And moving into the second image, you can see that initial reconstruction result. And then in the third image, we input the initial soil profile into numerical model to simulate the seabed flow under rainfall condition. At the same time, we have generated the monitoring data, which represent how seabed flow actually behave in the field. This image showing you that the core of our framework, this is the polar pressure evolution with time. We compare the numerical prediction results, which is the red solid line, with the monitoring data, which is dashed line, and apply the genetic algorithm to select the best low performance. So as you can see, as the time progresses, the difference between them is reduced, indicating that we get the better solution. Detail of the borehole at a target location that you can see over here. At the time progress, the red line solution closely match with the hidden ground truth, which is the blue dashed line.